Hello, I am Trevor Seets. Today I will be presenting our recent work on motion-adapted deblurring with single-photon cameras. As many of you may know, when you take a long exposure image of something moving, the result will end up blurry. However, if you take a short exposure image, the result may be noisy. In this way, a blur-noise trade-off is created through the exposure time. The current wisdom on dealing with this blur-noise trade-off is to take a burst capture, where many short exposure images are taken in rapid succession and later merged to get a low-noise, low-blur image. However, you must choose the set of exposure times somehow, which may require knowledge of scene motion and brightness, which makes the exposure times difficult to choose a priori. Additionally, it may be impossible for a single set of exposures to capture all the information of different moving objects. In this work, we propose a method where exposure times are chosen after capture on a per pixel basis by detecting apparent motion. In order to do this, we use single-photon avalanche diodes, or SPADs. SPADs have extremely high frame rate and are sensitive to individual photons. The output of a SPAD array is shown on the left, where in each SPAD output frame, each pixel measures the arrival time of the first detected photon. On average, dark scene points have long timestamps and bright scene points have short timestamps. Each timestamp, while very noisy, is essentially devoid of motion blur. We can leverage this data to combine photon timestamps along spatial temporal motion curves after capture time to create a deblurred image, such as the one on the right. First, let's look at a single pixel where we will detect motion in order to create virtual exposure times that both limit noise and blur. This plot shows the detected photon timestamps at each measured frame. Notice that by eye it is easy to see a few distinct regions. For example, this region with high average photon timestamps occurs when the fan blade is out of this pixel, and this region with low average timestamps occurs when the fan blade is within this pixel. We call the edges between these regions flux changepoints, which can be detected automatically using statistical changepoint detection with either offline or online algorithms. In general, flux changepoints represent times when an object leaves or enters a pixel, or when lighting changes in the scene. Flux changepoints represent the edges of our virtual exposure times. We aggregate the photons in between flux changepoints to create a piecewise constant flux estimate. In this way, virtual exposure times are created that adapt to motion on a per pixel basis. Repeating this process for all pixels, we create the changepoint video, which is an object that can be sampled at any point in time to give a flux estimate of the scene. Because each pixel has individual exposure times, the changepoint video allows slow-moving objects to have longer exposures and fast-moving objects to have short exposures. The changepoint video does a good job of detecting high-contrast edges that are used to find motion within the scene. To find the motion, we sample the changepoint video at a variable frame rate that is informed by the changepoints themselves. We then use standard alignment techniques to find motion within the scene. Then the original timestamp data can be aggregated along motion curves to create a deblurred image. Our flux changepoint method is particularly helpful in challenging situations with a wide array of motion speeds and contrasts. For example, in this scene, a dark, fast-moving car requires a short exposure time to avoid being blurred, whereas the slow-moving car in the back blends in with its surroundings, so requires a longer exposure time. Because our method adapts on a per-pixel basis, both cars are able to be reconstructed correctly. With the increasing size of SPAD arrays, this work has a wide variety of applications such as night vision, fluorescence imaging, and robotics. For example, this work could be useful for a fast-moving drone navigating at night. Thanks for watching.